So let's take some time and look at the dot product in the context of calculating work. So as we've been getting familiar with work, we know that it is F dot D, and we've also written this as FD cosine theta. And so the purpose of this video is basically just to go through the dot product in a little more detail, because I know folks are at different points with this. So conceptually, this FD cosine theta, you can try and visualize this as imagining you have, a force vector and a displacement vector, and they have some angle theta between them. And you can think of this as sort of like the projection of one vector onto the other. Sort of how much, let me draw this a little bit bigger so you can see it. How much of this one overlaps with the other one. And sort of the extreme cases of this would be, if F and D are aligned, if they're parallel, then in that case, theta equals 0. And so it's the F dot D becomes just FD, because the cosine of 0 is 1. And then sort of the other, simple case would be if you have F and D such that they're perpendicular to each other, then this is also easy to calculate because it'll be 0. And that, of course, would be because cosine of 90 degrees is equal to 0. So the general case is going to be somewhere in between. So that cosine is you can think of that as telling you how much overlap there is. Okay, so some technical details with the sort of a math aside here with the dot product. So the dot product is commutative. So A dot B is the same thing as B dot A. This is not the same for all vector math operations, but it is for the dot product. It's also distributive. So if you have A dot B plus C, this is the same thing as A dot B plus A dot C. So this can be a useful property, both of these properties. So let's look at the dot product in vector component form to work out how it works. So what I mean is let's put it in terms of our unit vectors. So remember the unit vectors. Let's look at sort of the general case in unit vector notation. So, and recall, your unit vectors, if you're not familiar, you should get up to speed on these. The unit vector is a vector that has a length of 1, and the convention that we use is that the unit vector along the x direction is I hat, the unit vector along the y direction is j hat, and the unit vector along the z direction, z-axis, is k hat. Okay, so just sort of an aside there. If that is unfamiliar to you, be sure to brush up on that. So what we can do basically is let's write a sort of a generic A and B vector in terms of this unit vector notation. So you would have some component that's in along I hat. And we're just writing out sort of generic components along each direction. And we'll do the same with a v vector. Okay. And note, let's look at the dot products for the unit vectors themselves. So what I mean is let's look at I dot I. So what would this be? Well, we can evaluate this in terms of our definition of I cosine theta, the angle between them. So if you do that with a vector itself, the angle between those would be 0, so this would be 1. Since this is a unit vector, the magnitudes of these are also 1. So this whole thing is just 1. In other words, I dot I is 1. And that's going to be the same, the same story for J dot J and K dot K. K hat dot K hat, sorry. J hat dot J hat. Those will all give you 1 when you take their dot product. So the other case that we would want to consider is, what happens if you look at, for example, I hat dot J hat. So in this case, let's do the same reasoning here. The magnitudes are both 1, but now the cosine of the angle between these, well, these are along the x and y direction. They're perpendicular to each other. So this theta would be 90 degrees, in other words. So this is 0. So I dot j is 0. And this is going to be the same story for any of the other combinations, I dot k, as well as, j dot I, or sorry, j dot k. Any of the combinations of unit vectors where they're not the same vector, you take their dot product, you're going to get 0. So this is sort of just a piece of information that we want to have when we go to look at the generic case of A dot B. So let's do that next. So if we look at, if we look at A dot B, what is that going to look like? Well, let's just write it out. We have AX, AY, B, times B components. Okay, and so what you would do is you would FOIL this out, just like you were, multiplying stuff together, and we would have, because remember, it's distributive, AX, BX, I dot I hat dot I hat. So notice that is going to give you 1 plus, and you can quickly see here what's going to happen. You'd have AX BY times, I hat dot J hat. That's going to give you 0, so this thing would be 0. Plus, we'll kind of go through it in gory detail for the purpose of this sort of reference video, but AX BZ I hat dot K hat, that one would give you 0. And then we would have to do the next set of terms, right? So notice AY BX is going to give us 0 because we'd have J hat dot I hat. Plus AY BY, that one will give us a value. Those are the, the y terms. And then AYBZ, that term would give us 0. And then we have AZBX, that would give us 0. K hat dot I hat. AZBY would also give us 0. They're perpendicular. And so the only other one that's going to survive is BZ. So apologies for going into gory detail with this, but I wanted to show you all the steps for this once. So look what has happened. If we consolidate, ditch everything that's 0, we're left with AX BX plus AY BY plus AZ BZ. Now notice all of our unit vectors have dropped out. They've turned into 1s. And this is how the dot product works, sort of for the generic case. And notice we've gone from a vector dot a vector, and this quantity doesn't have any unit vectors anymore, so this is scalar. And this is what we expect, right, with the dot product operation. So let's, so yeah, just to be super explicit, these would become 1. All right, so let's look at some examples. We'll look at sort of a generic math example, and then we'll look at a more physics-oriented example. Because remember, it's easy to get kind of lost in the detail of the math. The whole reason for us doing this is that we wanted to understand how to compute work when we have it in terms of a dot product, rather than just FD cosine theta. So let's we'll try not to lose sight of that by looking at an actual physics example. But first, let's just look at sort of a generic math problem. So this isn't displaying quite right. This should be a dot. Sorry. Let's just look at one of these because they're kind of similar. So let's look at A dot B plus C, the first example here. Okay. So what is this going to look like? Well, let's just put in A and B and C. We're going to have the 9.0 minus 8.5 dotted with B. So B is negative 8.0 I hat plus 7.1 J hat plus 4.2 K hat. And then we're adding to that C. C was 6.8 I hat minus 9.2 J hat. So let's consolidate the common pieces here in the B plus C side of this. So what do we have here? This would be this. In other words, this side we'll just leave alone. So we have negative 8 I hat and positive 6.8 I hat. So this would be negative 1.2 I hat. If we combine these together. And then we have 7.1 J hat and negative 9.2 J hat. So this would be minus 2.1 J hat, combining these together. And then we have one K hat piece, 4.2 K hat. And so let's do the dot product now. Let's multiply the pieces together. We would have the 9. So 9 times negative 12 I hat pieces, I hat dot I hat, plus, notice all these other ones are going to go to 0. 9 I hat times negative 2.1 J hat, since those are perpendicular, that goes to 0. And likewise with I hat and K hat, that one will go to 0. So then we have let's move on to the Y piece. So we would have negative 8.5 Actually, let me just write it like this, plus negative 8.5 j hat times negative 2.1 j hat. And so the j hat dot j hat will give us 1. And then notice we don't have a k hat piece here on this side, so you could think of that as 0 k hat. So there won't be any k hat contribution because, in other words, this would be 0 times 4.2 k hat. So this piece would go to 0. And we're left with these two pieces. So this 9 times negative 1.2 would give us negative 10.8. And this negative 8.5 times negative 2.1 would give us a positive 17.85. And then we add these pieces together, and you would get a final result of 7.05. And this is the result of, this combination here. We've gone from combinations of vectors to a scalar. Now this is just sort of an arbitrary math problem, but that's what we expect if we're doing, something dot product oriented. And you could, if you want to practice this, you could look at these other examples, which are just different combinations of these vectors. But hopefully this helps you see kind of what this looks like when you go to actually evaluate a problem. All right, so let's look at, so that's sort of just a math example. Let's look at a more physics-oriented example. Room here. So in terms of a problem, let's check this one out. We have a net force given by the following expression with components in I, j, and k, kilonewtons, and it's going to act on a small object of mass 95 grams. And the displacement of the object is d equals 5 I hat plus 4 j hat. And we want to find the work done by the force. And we also want to find the angle between the force and the displacement. So let's try and sketch this just to get a little bit of insight. This is going to test my powers of drawing here, but suppose we have x-axis, y-axis, z-axis. So let's see, the force. So it's a little bit artificial because we're plotting force and displacement on the same plot, but the purpose of this is just that we want to be able to visualize the angle between them. So let me do this in two different colors, and we'll try our best to kind of visualize this. So first, let's see the force. Let's do the force in blue. So the force is 10 in I, 9 in J. So this, you can tell this is not going to be particularly quantitative, and 12 in K. So it's a vector that would point sort of like that. Okay. And then, so yeah, maybe this could be 10, this is 9, and this is 12. And then let's plot the displacement vector as well. So this is a different, it's different units, but you get the idea. So this would be 5 in I and 4 in J. And notice it doesn't have a k component because there's nothing in the z direction. So this would be a vector that's just in the xy plane. And when we go to try and visualize the angle between them, we're talking about this angle. So the angle between F and D. So like I said, the purpose of this is just so we can try and visualize that angle to see what we're up to. So now let's do the actual computation. We want to take the dot product between F and d because we know that work is F dot d. So let's just write it out just like we did before. I hat plus j hat plus 12 k hat. And then our displacement vector. There's no k hat component. Multiply the pieces together, so we're going to have 10 times 5, 50 from the I hat components. 9 times 4, 36 from the j hat pieces. And then 0 from k hat because there's no, there's 0 in the displacement vector in the z direction. So this tells us that we have 50 plus 36. This will be 86 kilojoules, because if we look at the units, this force was in units of kilonewtons, and this displacement was in units of meters. So meters times newtons would be joules. Meters times kilonewtons would be kilojoules. And so the work is 86 kilojoules. And then the other thing that we're looking for is what is the angle between these. So now that we know what the work is, we can do the following. We know that work is F dot d, and we calculated it this way, but we also know that work is F d cosine theta. So if we're looking for the angle, we can just solve. So now that we know this, we can solve this for theta. So in other words, cosine theta is going to equal the work divided by the magnitude of F times the magnitude of d. So then the question becomes, well, what is the magnitude of F and what is the magnitude of d? And to get that, you can, just recall that you need to, sum the squares of the components and take a square root. So in other words, the magnitude of F would be the square root of fx squared plus fy squared plus fz squared. And the magnitude of d would be the square root of, dx squared plus dy squared. So let's do that. This would be, and let's put all our numbers in here. This is 86 kilojoules divided by the square root of 10 squared plus 9 squared plus 12 squared times 5 squared plus 4 squared. And when you crunch the numbers here, you would find that cosine theta equals 0.745. Keep track of the proper units. So these are in kilonewtons or whatever. And then, so if you know that, then all you have to do to get the angle is take the arc cosine, inverse cosine of 0.745, and we would find that theta is 42 degrees. So this angle up here, theta is about 42 degrees. So this is kind of cool. We're able to get another piece of information by setting equal the result of our dot product calculation from above to this other expression, FD cosine theta, that we had used before. So, and we were able to get the angle out of that. So I think stuff like this pops up in your homework, and so hopefully this helps you solve those kinds of problems.